Hello, everybody. My name is Gosia Konwerska, and I'm a developer for probability and
Hello,
statistics at
everybody.
Wolfram Research.
My name is Gosia
And
Konwerska.
I'll talk about some of the new features in version 12. This release was somewhat a potpourri. There were many various new features. Mainly, the new additions and improvements focus on how the data is located in space and time. And what we're looking at is our what we nicely call marketing page for the new features in version 12. And I think the easiest to enumerate those is to look at the bullet points that are here. So what we did, we introduced a new robust location measure, which is called spatial median, which supports numeric and geodetic data. We introduced new central features, new function, and this works with different types of data, not just numeric. We have robust measures for data with outliers, and these are also robust dispersion measures. And um, all this robustness can be seen here in the guide to the robust descriptive statistics for more information. Um, Another features, we have two new parametric distributions. One is Pareto Pickens distribution, which is a heavy-tailed and used to model exceedance and tails, heavy tails especially, and Hjord distribution, which is used in reliability modeling because it has a very flexible hazard function that admits bathtub shape, depending on the choice of the parameters. We added also some support for the hypothesis test of dispersion, completed support for the estimation of matrix distributions. You've never seen the matrix distributions in Wolfram language, that we also have a guide page for these. So all the collections for the matrix values distributions, and then special property distributions. And all of these work in the probability and statistics framework as a distribution. So they work with expectations and probability, and also with random variate for simulation. And then we have some speed ups for the computations of descriptive statistics and simulation estimation of parametric distributions, and a little improvements with processing of time series. All of these are featured in the examples here. And this is a nice matrix of examples. Each row is kind of themed in some way. The first row, it's the spatial medium central feature. Second row talks about the robust measures of location and dispersion. Third row, it's about the new distributions and also a little example on the hypothesis test. Next row, example on the matrix distributions, and then showing some examples where our computations are faster when comparing with the previous version 11. And the last row, it's all about processing time series. So what I would like to start is to show some examples of robust statistics. And so let me say why we actually need a robust statistics where we can have mean. But the problem is that sometimes mean is useless. And this is an example of a distribution for which the mean is not defined. So we cannot really tell anything about the location here because we cannot really operate on the mean. This is an example of a heavy-tailed distribution where the most of the weight is in the tail. And this can be seen when we compute quartiles. And you can see how the last quartile goes far to the right. And so what can be done is to, say, cut the tail off and compute the mean after truncating 10% of the distribution. So in this way, we'll see that trimmed mean is the new function, and takes in the distribution and then the pair of numbers. And the 0 refers that we do not truncate on the right because this distribution doesn't have tail. Sorry, on the left doesn't have tail, it only has tail on the right, and that's where we discard the 10%. And this corresponds to the truncated distribution. So we can create a truncated distribution from our original distribution and compute the mean. And you can see that for any, really for any truncation, so this is the little a, we can find the corresponding truncated distribution with appropriate quantile over there. Another thing, not just trimming, we could also consider clipping our distribution, and that's what it's called in this case, Windsorized mean. Compute Windsorized mean. So that means that we are clipping at the 10%, and this corresponds to censoring. So computing the Windsorized mean of a distribution means that we are computing mean of a corresponding censored distribution. And this again can show that for any A on censoring, we can find a corresponding censored distribution. And you can see the values are changing. Truncated mean, trimmed mean from the truncated distribution 27.5, Windsorized mean 74. So it really goes up, and we see that there is a difference between discarding 10% of the largest values and clipping them. So this is where you plot both of the means with respect of the, how much we clip from the tail. So you see the difference between them. And this basically shows us that that this difference is significant. So it tells us that this distribution has this heavy tail. And I want to throw here some, I wonder if it's gonna come up nicely here, illustrations for this to kind of tell you. So if we truncate, we basically discard everything that it's outside of our threshold. And when we censor, we kind of put all the values, assume that all these values have the value on the boundary in this way. And this basically, it's this example, which also has a list of all our robust location measures and robust dispersion measures in here. Just like this. Okay. So that was why we need robust. And we have here another example that show us why actually the robust measures are good and useful and maybe better in these situations when we have heavy tails. So here we consider a Cauchy distribution, and we can compare, the plot of the PDF with a normal distribution, which we know it doesn't have the fat tails. So here it's just the code for the plot, and you can see how little, like how small the tails of the normal distributions are versus the Cauchy distribution. Mean of the Cauchy distribution is indeterminate, and what we would like to do is to see how it behaves for samples. So if you sample from the Cauchy distribution and then compute mean, median, and by-weight location, so mean is non-robust, median robust, and by-weight location robust, you can compare the spread of these statistics. And you can see that the mean is all over. And when you look at compared to the same samples and taking the same statistics on the mean, median, and by-weight location on the normal data, and you see they're all behaving the same, they're all together. And this shows us that basically that median and by-weight locations behave better for the heavy-tailed distributions. Okay, so how can we use the robust statistics? Some of the data, we know that it's not coming from nice distributions like a normal distribution. We know it has the heavy tails, and in that way, using the robust statistics gives us some more information about that. So here is the data, which is and some income data. And the first thing I want to do when I have data to analyze is to actually plot, because as we just saw, that taking the mean might not be representable information about that. And what you can see here on the histogram is that it has the long tail. You can see the income extending far to the right. And so what is the mean? It's not really representative for this data. If you compute the median, we're gonna get somewhere better because we are in the middle of all the observations. What does the trim median tell us? That's Windsorizing means it's larger because we are censoring the data. We can also compute income for an average person, which is in the bottom half of the income distribution. So here we trim the data at half, so at 50%. And this plot should give us some more idea how all these means are located and give us the information about the locations, such. Okay. The next thing I want to talk is to introduce the spatial median. And spatial median is also a robust location measure, and it does operate by taking the minimum total distance to every point in the data. So it gives us the new location. And if we consider some random data, this is how it looks like. We can compute the median, and median operates point-wise and component-wise. This is exactly the same. And the spatial median uses the Euclidean distance by default. And we can specify what distance function to use in a spatial median. It could be L1 distance, which is called Manhattan distance in Wolfram language. And this is our answer. As you can see, this agrees with the median. And now, where are they located? So there is a little green point behind the red point. So there is slight difference in the location. So spatial median operates on the Cartesian coordinates, but also operates on the geopositions. And let's consider all the cities in the state of Pennsylvania. This might take a little bit, but hopefully not too much. Pennsylvania is not a desert, so it has some fair amount of cities. Okay. Okay, and then we're gonna extract locations for these cities, and then can visualize using geographics. Right, so these are all the cities. Let's compute the spatial median, just input locations, and it returns the geo position of the spatial median. And this, of course, is just finding a place which it's central in a way to all the locations of the cities. But it doesn't take into account anything else, just the locations. And when we think about cities, we usually also have to take into account the population. And so that's what sometimes maybe it's known as a population center. So what we would like to do is to find the population of the cities and then add this information to compute the spatial median. Okay, so this is the range of the populations. And so this is the way to compute spatial median with weights. It's basically by constructing a weighted data with our locations and then the weights, and in our case, these are the populations. Okay, and the question is, where is this location? And so it's a bit far more to the southeast. And when we compute the geo distance between the two, we see that it's non-zero. It's 80 some miles. And Also, what I would like to say is that geodistance will be a default um, distance function for data that it's given as the geoposition. So that should give us true. Okay. So this is working with geopositions. As we saw before, I was extracting the coordinates of the locations. If I can go up here, coordinations, and then apply a geoposition. Okay, and why do I not work with the coordinates? Because if we just work with the latitude and longitudes and Euclidean distance, that's that's not the right way to go, because as we know, Earth is not flat. It is fine to use the tangent plane for the local approximations, yes, but if we look at, for example, cities around the globe, like this, right? And then once you do find the positions, once you look at the longitude and latitudes and find, as I call, wrong median with them, and then compare it to the other median, you see that that's a huge difference. And let's see. Okay, so so we have, you can see them that they are far apart. Okay, and if you cannot really see on the map, then we can use this nifty feature, which is find the geo nearest country next to the wrong median and to the spatial median, right? So one is close to Portugal, one is close to Norway. It's far apart. One note I would like to make here is in this computation of spatial median, there is an option max iterations, and this is because spatial median indeed is a optimization function. So this is an option for the optimization. Okay, so that was about spatial median. Central feature, it's similar in the way that it minimizes the distance, but it finds the point within the data that minimizes the total distance to every other point. So it does not produce a new location, it just selects the point within the given data. So, oops, great. It's good to have undo. So let's try again. So we have some data. We can find a central feature of data, which just returns the data point. We can ask central feature data goes to automatic, which is going to give us a position of the central feature in the data set. Or we can say data goes to whatever set of labels we would like to assign or values, and it's going to give us this value. So for some application, let's look at another state, Florida, for a change. I'll look for the 10 largest cities in the state of Florida. This definition of polygon is just to make our geographics nicer and plot the state. So these are the cities. So what is the central city among these 10 cities? So this is a question for exactly for a central feature. And here we want to know this kind of a geocenter, so we use the geodistance. Okay, so that's Tampa. But we are looking at the cities, and when we have to go from one city to another city, we just don't go across the swamps and such, just use the roads. So in this situation, I think that more useful would be to find what we call travel center and use a distance function, which would be a travel distance, which is in this case traveling by road, so the driving distance. And this gives us completely different town. We can compute travel paths, and we can illustrate now where we are in Florida. So the green is Tampa, the red is our travel center, and the red are the driving paths to get there. Now, it's the same deal as we had before with Pennsylvania and the cities. Again, we might take into account the population of the cities and compute um, the weighted data, so the locations with the populations being our weights, and then find the geocenter based based on a geo distance and the weights. And then we can also find what I called weighted travel center, which is a central town based on the travel distance and also taking into account the weights of given by the population. So in this case, they both agree. So it means that the weights of the population really pushes this to give us a different answer than without the weights. So and we can visualize that. And Orlando, it's our weighted travel distance center. I said before that central feature can be used for different inputs, not just numeric and geopositions. And so because it chooses a point in the data set, it doesn't create anything new. So if the data set can be ordered, or can we define a distance function for our data set, then we can use a central feature. And I want to look at example of text. So what I have here is a list of main Slavic languages spoken today. And what I would like to do is to translate word tree from English to all these languages. And then I would like to find a Slavic tree, so the word that it's essential to all these Slavic words for tree. And this for the text, it's using edit distance as a distance function. So now this is drvo, and the question is, which language is using that? So we can find all the languages that use this word, and this seems to be Macedonian. Now, what we can do is to switch from just the words to images by the means of rasterization. So rasterize the words, right? And so now we have images, and then find the central feature of this images. And what central feature will do is to first use conform images, and then use image distance as the distance function. So now we have a different word, drzewo, and this happens to be Polish. Okay. So this is more or less all about the robust statistics and spatial median and central feature. And I will now introduce new parametric distributions. So we'll talk first about the Pareto Pickens distribution, which is also known as the generalized Pareto distribution. And it was originally introduced to study extreme order statistics. And it can be also used to model exceedance for power tail distributions, and many of such distributions exist in Wolfram language. And we've seen already Pareto, and we've seen Cauchy. There is also the gamma distribution, or Dagum, and many more. So what I will do, I will create a sample from a Dagum distribution. And we compute moments for this distribution, we kind of see that the moments are only defined for error r, so the order less than 3. So the higher order moments just do not exist. And when we plot the histogram for this data, we see this is specifically set with plot range O. So you see that most of the plot is actually empty visually, but that's not really true because there is this long tail that happens. So there are bins that are far to the right. And what we can do now is to take a quantile, so this is 95%, and then compute the tail. So we take all the data which are larger than the 95% quantile, and then feed tail data to Pareto Pickens distribution using estimated distribution. Okay, how do you know if this fit is actually any good? One way is to plot a histogram of the tail data against the PDF of the estimated distribution. And this gives us some hope and visual confirmation that this is indeed a good fit. Another thing is to use a quantile plot, so data against the estimated distribution. And another one is to run the distribution fit test, which is just testing the goodness of fit. And conclusion tells us that the hypothesis is not rejected. The second new parametric distribution is the Hjort distribution. And this distribution is used in reliability to model lifetimes of some devices. It is used because it has a hazard function that can be shaped as a buff type shape. And this corresponds to higher failure probability during so-called burn-in period, which then lowers and then again raises with age and continuous use of the devices. And so here, let's have a look. Wrong order of things, but maybe not. Okay. So define the hazard function for your distribution in terms of the parameters, and then define few cases for some choice of parameters and just we can illustrate. So you can see it can be increasing, decreasing, constant, or has this desired buffed up shape. Okay, so we can consider a device that has a lifetime modeled by Hjort distribution, and we can plot a hazard function of this model. It has the buffed up shape. And so to avoid early failures, the equipment is operated during this burning period. And we would like to find the probability of failure within the first year, which usually is the warranty period. So what I would like to do is to define a new distribution, which is quantity distribution, which will give us the reference of time frame. So we are looking at years, and then find the probability that equipment fails within the first year. We can also ask question, finding the length of burning period after which the failure probability within the first month is reduced by half. So this equation. And we should find a solution using nsolve. Okay, so we have the answer, and then what's the burning period? It's 0.4 months. I really don't know how long it is, so I'm gonna convert to days. So that's 12 days. And another good question is, what's the expected lifetime of the equipment after it survived the burning period? So this is a conditional expectation, and you can see here that we have expectation of t under the condition that t is greater than our burning period, and t distributed according to our quantity distribution model. so almost 3.5 years. And also we can ask the question, what is the time that the equipment is most reliable? So it's 1.2 years, and then again, conveniently 15 months. So okay, so that's all about the distributions. And another topic I would like to talk about is time series and time series reprocessing improvements. And so what we have is the improvements really to how time series window and time series resample operate. And we know that the time series window selects a part of the time series depending on the specified window. And right now we can specify this with a day specification. So let me create a very simple time series in terms of the values, but the dates happen to be around Easter in 2017. So I can ask about subsampling this for the federal working days in Germany, and I can achieve that by specifying a holiday calendar in time series window, and then the window to be business day. What are the federal working days in United States? What are the working days of the New York Stock Exchange? Right? And then we need 2 lines to plot this. So you can see that every of this time series actually gives us a different answer in respect when what are the business days in different countries or according to a different calendars or schemes. Okay, for the time series resample, okay, let's create another time series, which is a bit longer this time. And we can, for example, specify just weekend as our day specification for the time series resample and extract the weekends, and to check, find the day names on the dates for this time series. So Saturday, Sunday. When we use time series window, we can also specify a given day of the week. So let's say I would like to have only the data that's on Tuesdays. And here we go, Tuesday, Tuesday, Tuesday. And we can apply this to, some kind of a real life data. So that's the financial data stock at close for Apple for some time. And what I'm interested in, for example, give me the values at the end of month. Right. And one thing may be interesting or not is like how many trading days there were for each month. Okay. And let's see. Okay. And I think that's going to be a last fun example, is that we have event series of the US president's birthdays. And this is including a current president. And if you wonder why it's 44, that's a bit of a trivia, because there was a president, a person who was twice a president, but not in consecutive terms. And hence it counts kind of twice, but we only have one birthday for that person. So we can plot the dates, and we can find the day of the week for each birthday. We look the moving map, and then we can apply a function on the window of single event and directly on the dates. and create an event series. And this event series doesn't tell us much unless we visualize that. So that's my pie chart of birthdays. You can see that Wednesday, it's not a popular birthday day, and Monday probably most popular. We can select, using time series window, all the birthdays that are on Sunday, and find all the presidents who were born on Sunday. And another fun question is to find what it's called shared birthdays. So find which presidents celebrate their birthdays on the same day. And we have 2 pairs of such birthdays. So, and if there are any questions, that would be also a good time for that. And no questions. Okay. So thank you very much for the time, and I wanna recommend having a look at more examples on our page here. So thank you very much.